Hi everyone, I'm Xiao Yidong from University of Science and Technology of China. Today I will share our recent work about improving contrastive language image pre-training with proper self-supervised design. First, I would briefly review CLIP. It uses image and its corresponding caption as input and uses a dual encoder framework to get the image and text feature. The CLIP has several advantages. First, it don't need expensive human annotation. All the data could be collected from the internet with simple filtering strategy. So it could use nearly unlimited data for the pre-training and shows strong scalability. Second, the contrastive loss aligns the image and text feature into the same feature space. So the backbone could not only use it in classical vision or language tasks, but also used in some vision language tasks. However, the CLIP is far from perfect. It views the image and text equally and uses a simple contrastive loss to align them. Such a simple operation ignores the data property difference between image and text. We think the image is continuous pixel signals which contains dense fine-grained semantic information. On the contrary, the text is discrete words, which has sparse semantic or different objects and could only describe part of the image. The contrastive loss aligns the global representation between them may lead the vision encoder only focus on the text-described objects and ignore the rest objects, which might be useful for the downstream tasks, and this is a waste of the model capability. Here we show some examples from the dataset we use. It can be seen that although the text describes the image properly, there are still many objects missed. So an intuitive idea is to introduce some additional supervision for the vision encoder and make it still focus on all the objects. And the well-studied vision self-supervised learning is a good choice. In the following, we first discuss combining CLIP with different image self-supervised learning methods and then introduce our MaskCLIP. The first choice is the image contrastive learning. The advantages of such combination is the vision encoder capability is enhanced, while it has two weaknesses. First, due to the central augmentation strategy used in the image contrastive learning, the model has to focus on the most salient object in the image, and its output feature is still a global representation of the image. This is the same as the CLIP, and the local representation is still missed. Second, the contrastive learning is two additional forward of the image encoder, so the computation cost is quite large and the training speed is slow. The second choice is the mask image modeling. Its supervision is a pixel-wise distance loss between the input image and the reconstructed one, so it is a local supervision, which is complementary with the global supervision in CLIP. Meanwhile, the encoder only sees a small part of the input and the decoder is lightweight, so the computation cost of the mask image modeling branch is small. However, there are also some weaknesses of this method. As previous was analyzed, pixel value is not an efficient prediction target, and it makes the encoder to memorize some unnecessary low-level information. It is a conflict with CLIP that only focus on high-level semantic information. By analyzing the combination of CLIP and the current image self-supervised learning method, we find a desired self-supervised learning method should have the following properties. First, it should be a local supervision on each token, so that it could learn fine-grained semantic and be complementary with the CLIP global representation learning. Second, its supervision should be a high-level semantic supervision, so that the pre-training is much efficient and the output is consistent with CLIP. We use mask image modeling for the first property and mean teacher self-distillation for the second property, and we have our new method named mask self-distillation. It can be seen that we use a momentum encoder to provide the feature prediction target, so that the supervision is local and semantic. Furthermore, we also aid the MaskCLIP language modeling in the text branch to further improve its performance. Then we conduct several experiments to prove our analysis before. First, we compare the results of CLIP and different combinations. Here we consider three methods: the contrastive learning-based method SimCLR, the mask image modeling-based method MAE, and our MaskCLIP. We have several observations. First, the vision supervision is helpful for the CLIP. All the combination improves the results on both image tasks and image text tasks. And our MaskCLIP shows the best performance on all the tasks. Then, when it comes to the efficiency, as we analyzed before, the contrastive learning-based method has much larger memory cost and slower speed, while the mask image modeling-based method is much efficient. We also show some visualization results of different models. For a given image and its caption, we show the similarity between the text feature and the image feature before the last pooling layer. We can see that all the methods show high similarity between the image and text. This means they all align the image and text feature properly. Then we select the nouns from the caption and prompt it to new text, such as a photo of teddy bears, and we show their similarity with image tokens. We have different observations that for MAE, it fails to disentangle the white teddy bears and the snow. This may be because its training supervision is pixel. It do not have semantic information and leads the model to use color as evidence. On the contrary, our MaskCLIP works well. This proves that the mask self-distillation helps the model to learn better semantic representation for local patches. At last, we compare our MaskCLIP with previous method. To reduce the influence of data, we train all the methods with the same CC 50 million dataset. We find that our MaskCLIP outperforms the baseline method, MAE, and CLIP with a large margin. We further test the zero-shot classification performance on 20 small datasets from the image classification in the wild challenge, and we won the first place. For image text zero-shot retrieval, our MaskCLIP also gets the best result. Thanks for your listening. Goodbye.